Good evening and welcome to the live sessions for the course on computational science and engineering. It is 6 p.m. but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Good evening. Good evening, and welcome to week 8 of the live sessions for the course on computation science and engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of the Department of Aerospace Engineering at IIT Kanpur, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. So, in this week, we have been working with various numerical integration and differentiation techniques, and some of the more common ones might be already known to you, such as the trapezoidal rule or the simple Simpson's third rule and others. And however, we'll be looking at some of the more varied and more uh, used numerical integration and differentiation techniques that find application in engineering problems. And well, all of these methods actually are or stem from one generalized method called the Newton's codes methods. And again, these Newton codes methods can be of two types. They can be either open or closed. So when, say, as we can see on the figure on the right, if we are working in this interval a comma b, where it's a closed interval, so both the endpoints are included. Whether we are including these endpoints in the numerical differentiation scheme as well or not decides whether the method is open or closed. If both the endpoints are included in the calculations, then it's a closed method. And some examples of which are the trapezoidal rule and the Simpson's rule. And if the two endpoints are not included in the calculation or in the analysis, then it is an open method because then effectively the numerical technique is basically only operating on the open interval a comma b rather than the closed interval as originally given. Now, Professor Day has already spoken at length about the theory and maybe even the origins of these Norton codes methods. So we'll just quickly refer to some of the standard formulae. And from the generalized Newton codes methods, the closed Newton codes methods, depending on the value of the parameter n, and the different formulae may emerge with different specified names, such as for n equals 1, the closed Newton codes method is called trapezoidal rule, formally stated here in equation 4.25. Integral from x naught to x1 fx dx equals h by 2 times f of x naught plus f of x1 minus h cube by 12 f double prime or the second derivative of f at zeta, where zeta is a point between x naught and x1. What we're trying to actually do in any numerical integration technique is to find the area under the curve for relatively simple geometric curves such as a straight line or say a well-defined parabola, ellipse, or even some trigonometric functions, the derivatives and antiderivatives of which are well known, such as the sine and cosine functions. Finding this area under the curve can be relatively simple. However, when you are working with abstract curves or those with complicated geometry or curves which are expressed by functions which are not elementary integrals or even piecewise functions where the exact mathematical form may not be known. In such cases, we must resort to numerical integration schemes, whereby what we are doing is we divide this entire domain A comma B between the two purple arrows into very small uh, zones uh, or steps, and clearly the size of one step is just simply called the step size. In this case, it is referred to by h. And if we can divide it into a number of fine enough steps, then we measure the area that this histogram contains. And if the step is very fine, we can see that the histograms will fit more and more closely with the actual given arbitrary curve. For very coarse step sizes, the error between the area enclosed by the curve and the area enclosed by these rectangles or histograms will be significant. However, with increasing number of steps and decreasing step size, the two areas can match rather closely. So for n equals 1, the closed within quotes method is simply given the name of trapezoidal rule, because in a way we are trying to find the area of a trapezoid. We would remember the formula for area of a trapezoid, which is uh, half into perpendicular distance times the sum of parallel sides. And here it is something similar: f of x naught plus f of x one times h by 2 minus h cube by 12 f double prime of psi, where x naught less than psi less than x1. When the parameter n equals 2, the numerical integration scheme takes on the name Simpson's rule. And here, rather than just using the two endpoints x0 and x1, we have a third integration point. And thus here we are working with 3 points: x0, x1, and x2. And the formula as given in equation 4.26 is integral x0 to x2 fx dx equals h by 3 times f of x0 plus 4 times f of x1 plus f of x2 minus h power 5 by 90, fourth derivative of f evaluated at xi, where x0 is less than xi less than x2. In this case, we see rather than just a simple average, as was the case in trapezoidal rule, here we have a weighted average. Now, we might have encountered the trapezoidal rule and the Simpson's rule in our elementary numerical methods course during any engineering or other mathematics or science related curriculum. However, some of the methods that we will encounter in the upcoming slides need not be so common. When the parameter n equals 3, we obtain the Simpson's 3/8 rule. And here, whereas previously in Simpson's 1/3 rule, we were working with 3 integration points. In trapezoidal rule, we had only 2 integration points, which were the endpoints of the interval. In Simpson's 3/8 rule, we are now working with 4 integration points, those being the two intervals, the two endpoints of the interval x0 and x3, and additionally 2 points in between x1 and x2. Also, typically, the domain will be divided equally between these various integration points. That is, the integration points will be placed symmetrically with respect to the interval ends. So, when n equals 3, we obtain Simpson's 3/8 rule. Integral x0 to x3 fx dx equals 3h by 8 times f of x0 plus thrice f of x1 plus thrice f of x2 plus f of x3 minus 3 by 80 times h power 5 fourth derivative of xi, where xi is a point between x0 and x3 as given in equation 4.27. Further, when the parameter n is further increased to 4, We now have an additional integration point, and the formula takes on the form integral x naught to x4 fx dx equals 2h by 45 times 7 f of x naught plus 32 f of x1 plus 12 f of x2 plus 32 f of x3 plus 7 f of x4 minus 8 h power 7 by 945 sixth derivative of f evaluated at xi, where xi is a point lying between x0 and x4. We see that as we increase the number of integration points, the term that is subtracted from the integral and which is supposed to take care of the error of approximation between the actual area of the curve and the measured area, we see that the exponent of the step size in these terms keeps on increasing as the number of integration points increases. Of course, for while the step size will also keep on changing, we can see that for a small enough step size, this error is also very small because we are raising a small number to a positive exponent. The closed Newton cotes method formula for four integral points does not have a specific name, and it might not be very frequently encountered in mathematical analysis. However, just for the sake of completeness, we are mentioning it here. Next, we encounter the open Newton cotes methods, where, as we discussed before, we are working to find the area under a curve. We are given either the function of the curve and the endpoints of the interval. And in a closed method, our approximation formula also includes some calculation or some expression based on the endpoints. However, in the open Newton cotes methods, we do not really include the endpoints and only work on the open interval AB as opposed to the closed interval AB of the closed Newton cotes methods. When n is equal to 0, the generalized open Newton cotes method formula takes on the form of the midpoint rule. Integral x minus 1 to x1 fx dx is equal to twice h f at x naught plus h cube by 3 f double prime at xi, where x minus 1 less than xi less than x1. Clearly, what we are doing here is we have moved the origin of our coordinate system to the midpoint of the interval, and we are denoting the left endpoint of the interval as x minus 1 and the right endpoint as x1, thereby denoting that the point x naught on the midpoint is placed symmetrically between the two endpoints. And what we are basically doing is simply taking uh, twice the function value at the midpoint, multiplying it by the step size, along with some error term. And here the errors are added because since we're not really making use or calculating at the endpoints, it is estimated that the area will end up measuring might be somewhat less than the actual area under the curve. And so, whereas in the closed Newton cotes methods, we were actually subtracting some quantum of area, here we are adding a small amount. Similarly, when the parameter n equals 1, the formula takes the form x minus 1 to x2 fx dx equals 3h by 2 f of x naught plus f of x1 plus 3h cubed by 4 f the second derivative of f at xi, where x minus 1 less than xi less than x2. Similarly, we have the open Newton cotes methods for the value of the parameter n2 and 3. When n is equal to 2, the formula becomes integral x minus 1 to x3 fx dx equals 4h by 3 twice f of x naught minus f of x1 plus twice f of x2 plus 14 by 45 h power 5 fourth derivative of f at xi, where x minus 1 less than xi less than x3. When n equals 3, the formula as given in equation 4.32 takes on the form x integral x minus 1 to x4 fx dx equals 5h by 24 11 times f at x0 plus f at x1 plus f at x2 plus 11 times f at x3 plus 95 by 144 h power 5 fourth derivative of f at xi, where once again x minus 1 less than xi less than x4. And just to compare both the closed and the open Newton codes method, along with the various values of the parameter n, here is a comparison of the evaluation of the area under a simple or elementary integrable plane sin x between the in the interval 0 to pi by 4. And the reason for the choice of this function was because it can be easily calculated, and so we already are aware of the exact area that this curve encompasses, and so we can have a very good estimate of the performance of our numerical methods. So we have the value of n starting from 0, 1, 2 to up to 4, and the first row contains the estimate of the area as approximated by closed Newton codes formulas for various values of n. We see that with increasing n, the error decreases significantly. Especially we see that for n equals 1, the and comparing it to n equals 2, for the closed Newton codes method, the the error goes down by 2 to 3 orders of magnitude, by 3 orders of magnitude to be precise, and it further halves when n is equal to 3, and when n equals 4 it goes down by up to 3 orders of magnitude again. So there is a clear effect of increasing the number of integration points when we are working with a closed Newton codes formula. For the open Newton codes methods, on the other hand, we see that the effect of increasing the number of integration points from 0 to 1 does not have any appreciable effect. However, from 1 to 2 and 3, the error does go down by 2 orders of magnitude. It is also clearly noticeable that the error for the closed Newton codes formula of order 0 is smaller than even the for the open Newton codes method of order 0 is less than even the first order closed Newton codes formula. However, this comparison may not be true in general because what we are working with here is just a very simple curve, and if we are presented with a more challenging curve or something more abstract, then uh, these errors might change. However, just for comparison's sake, we see that this is the complete picture. And in general, for closed unit codes methods, increasing the number of integration points will definitely improve the accuracy of the calculation. But then again, this has to be balanced against the computational effort that we are putting in and the cost and time of computation. So sometimes, depending on the error tolerance that we are willing to say endure, uh, reasonable error might be good enough for all intents and purposes, and we do not have a very fine or a very refined result. Okay. Till now, the Simpsons rules that we looked at, being the one third or uh, 3/8 rule, they were rather the simple form of the Simpsons rule. However, we also have a more robust and generalized form called the composite Simpsons rule, and it is stated here. So let f be fourth continuous on the closed interval AB, Let n be even, that is the number of integration points we want, and let the step size h equal b minus a by n, as is typically the case because we want to space our integration points, uh, say, uniformly in the given interval. Let xj be defined as a plus jh, where a is simply the left hand of the interval, h is the step size, and we are just incrementing the x locations starting from the left hand of the interval by the step size. Then there exists a quantity mu belonging to open a comma b, for which the composite Simpson's rule for n subintervals can be written with its error term as integral a to b fx dx equals h by 3 times f of a plus twice summation from j equals 1 to n by 2 minus 1, and remember n was stated to be even, f of x 2j plus 4 times summation from j equals 1 to j equals n by 2, f of x 2j minus 1 plus f of b whole minus b minus a by 180 h power 4 times fourth derivative of f evaluated at b. And here what we can notice is that the error term for the composite Simpson's rule is of the order of h power 4, whereas it was of the order of h power 5 for the standard Simpson's rule. And we can also write here in equation 4.27 as well as in equation 4.26. However, a direct comparison of these error metrics does not give us the complete picture, and it's not fair because for the standard Simpson's rule we have the value of the step size fixed, and this fixed or constant step size is simply b minus a by 2. However, for the composite Simpson's rule we have h equals b minus a by n, and thus the step size we have here, of course that being even, is far smaller. Thus this very small quantity raised to a higher positive power, or the same positive power, will result in a far smaller quantity. And what this does is permit us to considerably reduce the value of the step size h when the composite Simpson's rule is used. And right off the bat, we might be tempted to think that okay, if I can choose a very small step size and if I keep reducing my step size arbitrarily, the accuracy of my calculation will keep on increasing. However, what realistically happens is that after a certain threshold, the improvement in accuracy does not really is not really significant compared to the, and is simply not worth it compared to the computational effort which must be put in. And we will see that after decreasing a step size beyond a certain threshold, the error seems to saturate and does not really improve further. In fact, if we have too fine a step size, we might even run into other implementation side problems. And thus, it's not true that we can keep on decreasing the step size arbitrarily and end up with uh, a result that is more and more accurate. There is always a trade-off between the accuracy of the result, that is the error, and the computational effort. And we, as engineers, it is our job to uh, find the sweet point between these two opposite ends. Now, in general, the Newton codes formulae are generally unsuitable for use over large integration intervals. High degree formulae would be required, and the values of the coefficients in these formulae are difficult to obtain. What we also noticed in our previous session is that when we are trying to interpolate in a given interval with a very high order polynomial, they are prone to large fluctuations in very small intervals. That is to say, the value of the function will vary wildly in a very small space, which is not generally seen in physical systems. And there's a small fluctuation in the input to the system will result in large changes to the system's response, which is not really desirable and is often unphysical. Similarly here, the high degree formula would have coefficients which cannot be obtained easily. Secondly, the Newton-Cotes formulae are based on interpolatory polynomials that use equally spaced nodes, as we have just been talking about, that the interval is divided into uniformly spaced nodes, a procedure that is inaccurate over large intervals because of the oscillatory nature of high degree polynomials, as we just discussed. Further, based on, say, some intelligent guessing or some analytical reasoning, in some cases it might even be preferable to, in fact, concentrate our integration points in certain regions of interest, whereas uh, having sparser integration points in areas of non-interest or where we expect smaller fluctuations or smaller changes in the response of the system. This is somewhat similar to the concept of mesh refinement, where we use, for those of us who might have some preliminary exposure to the finite element method or the finite volume method, where we have uh, a far greater number of nodes in the region of interest compared to, say, a far away region where we do not expect the transient effects to be very strong. Okay, now we will use the Simpson's rule to approximate the integral 0 to 4 e power x dx and compare this to the results obtained by adding the Simpson's rule approximation for 0 to 2 e power x dx and 2 to the power 4 e power x dx. We also compared these approximations to the sum of the Simpson's rule for 0 to 1 e power x dx, 1 to 2 e power x dx, 2 to 3 e power x dx, and 3 to 4 e power x dx. And the reason behind these exercises, as we just saw, the Newton-Cotes formulas are generally unsuitable over large integration intervals. However, such the example or analogy of the large integration interval will be something like 0 to 4 e power x dx here. However, what happens if we break up this large integration interval into smaller intervals, such as half it or divided into two intervals, or even divided into four intervals? We'll solve this and compare the errors. But first, I would request the participants to take a minute to absorb the question and maybe even start solving them using the standard formula provided, and then we'll get on with the solution. So please take a minute to use the given formula to start solving the question. The integral again is 0 to 4 e power x dx. So let us get on with the solution. For the entire interval 0 to 4, the Simpson's rule for the function fx equals e power x with a step size which was given as h equals b minus a by 2, or in this case 4 minus 0 by 2, or h equals 2, will simply give us the value of the integral as 2 by 3 e power 0 plus 4 e square plus e power 4 equals 56.76958. And see here, rather than giving the equal sign, we are given the is approximately equal to sign because we are ignoring the error term. So approximately, as per Simpson's rule, the value of this integral will be 56.76958. However, since this is a very elementary integral, we can also solve for the exact area under the curve, and we find that it is 53.59815. Thus, the error between the exact value and the approximated value is 3.17143, and the Simpson's rule is overestimating this. If we break our given interval into two subintervals of 0 to 2 and 2 to 4 and apply the Simpson's rule, the integral we get is 1/3 e power 0 plus 4e plus e square plus 1/3 e square plus 4e cube plus e power 4, which equals 53.86385. And now we see that just by dividing the given interval into two subintervals, the error has already reduced by one order of magnitude. Now the error is only 0.26570. Further, if we divide the given interval into four subintervals, the integral will transform as, instead of 0 to 4 e power x dx, we are now working with 0 to 1 e power x dx plus 1 to 2 e power x dx plus 2 to 3 e power x dx plus 3 to 4 e power x dx. As per Simpson's rule, this will be approximately equal to 1/6 e power 0 plus 4 e power half plus e plus 1/6 e plus 4 e power 3 by 2 plus e square plus 1/6 e square plus 4 e power 5 by 2 plus e cube plus 1/6 e cube plus 4 e power 7 by 2 plus e power 4, which will sum up to 53.61622. In this case, the error is just 0.01807, and we see that the error has decreased by a further order of magnitude just by dividing the interval into four subintervals. Now, to be able to implement this composite summations method in a code, I will also be supplying a pseudocode, which you can formalize into a code depending on the programming language of your choice. The objective of such a code would of course be to approximate the area under the curve for any given function and given interval. The inputs which we will be requiring are the endpoints of the interval a and b, and the positive number or the positive integer, which is also even, into which we want to divide the interval. The output would be the approximate value of the integral or the approximate area under the curve of the function fx. In the first step, we set the step size, which is simply equal to b minus a by n, a and b being the endpoints of the interval, and n being the even positive integer into which we want to subdivide the given interval. In the second step, we set the value of three sums xi0 equals fa plus fb, where xi is the approximation of the integral line, xi1 equals 0, where it is the approximation of summation of f of x to I minus 1, and xi2 equals 0 is the summation of f of x to y, where if we refer to the composite summations rule again, we see these three integrals, one for f of x, one for f of 2xj, and one for f of x 2j minus 1. In the third step, we start a loop uh, for I equals 1, 2, 3 till n minus 1, and we loop through the steps 4 to 5. In step 4, we set the nodes. Thus x equals a plus ih. In the fifth step, if I is even, we set xi2 equals xi2 plus fx. Means we set xi1 equals xi1 plus fx. In the sixth step, we set xi equals h by 3 xi0 plus 2 times xi2 plus 4 times xi1. And in the seventh step, we finally output the integral or the area under the curve xi. After which, we ask the program to stop. Apart from the Simpson's composite rule or the composite Simpsons rule, there are a few other composite rules which may be of application. The first is the composite trapezoidal rule. We are familiar with the simple trapezoidal rule, but there is also a composite version of the same, and it is stated formally here. Let the function f be second continuous on the closed interval AB, and the step size h equal b minus a by n. See here that there is no restriction on n being even only, and xj equals a plus jh for each j equals 0, 1, 2 till n. Then there exists a quantity mu belonging to the interval open AB, for which the composite trapezoidal rule for n subintervals can be written with its error term in the following fashion: integral a to b fx dx equals h by 2 times f at a plus twice summation j equals 1 to n minus 1 f at xj plus f at b minus the error term, which is b minus a by 12 times h square times second derivative of f evaluated at mu. Again, we also have a composite form of the midpoint rule, and it is stated formally as follows. Let the function f be second continuous on the closed interval AB, let n be even, and let the step size h equal b minus a by n plus 2, and let xj equals a plus j plus 1 times h. For each j, this time starting at minus 1, then being 0, 1, 2, and so on till n plus 1. Then there exists a quantity mu belonging to the open interval AB, for which the composite midpoint rule for n plus 2 subintervals can be written with its error term as integral a to b fx dx equals twice h into the summation from j equals 0 to n by 2 f of x2j plus the error term b minus a by 6 h square times the second derivative of f evaluated at mu. Now we'll discuss a method of great practical importance, which is often used in the computer aided solvers, and it's called the RK method or the Rangutta method of order 4, uh, typically abbreviated as RK4. Professor Tay has already spoken at length about this method, so we'll just directly go to the formula. Here we are working with a few quantities. First of all, W0 must be given and it is equal to alpha. The quantity K1 equals H times F at Ti comma Wi, where H is the step size. Ti is the current time step. K2 equals H times function of Ti plus H by 2 and Wi plus half K1. K3 equals H times F at Ti plus H by 2, Wi plus K2 by 2. K4 equals HF times Ti plus 1, H times uh, F at Ti plus 1, and Wi plus K3. Wi plus 1 equals Wi plus 1/6 K1 plus 2 K2 plus 2 K3 plus K4. for each I equals 0, 1, 2 till n minus 1. This method has a local truncation error of the order h power 4, provided that the solution yt has 5 continuous derivatives. Further, we introduce the notation k1, k2, k3, k4 into the method to eliminate the need for successive nesting in the second variable of the function as a function of time and the space variable y. Now we'll use this RK4 method with the prescribed step size of zero point 0.2 and the prescribed number of uh, subintervals 10, and the time step ti equals zero point 0.2 i to obtain an approximation to the solution of the initial value problem. Y prime equals y minus t square plus 1, where 0 is less than equal to t is less than equal to 2, and the initial value of y at t equal to 0 is given as 0.5. So we see the very interesting property that the RK4 method is actually used for solving ODEs and initial value problems. Now, based on the discussions from some of the previous sessions, we should be in a position to also solve this given initial value problem analytically, or if not solve outright, at least be able to comment whether it can be solved or it has a closed form solution or not. So I will request the participants to just take a minute to absorb the question, to try to solve it or at least initiate the solution using the analytical methods, and then we'll get on with the solution of this problem using the RK4 method. Now, this is useful for solving equations of the form where the derivative of y is given as a function of the time variable t and the variable y itself. In the zeroth iteration, that is to say, before we can even begin iterating for the solutions, we must compute a few quantities which must be used as input to the solver in each iteration. So in the zeroth iteration, we must find the quantities W0, K1, K2, K3, and K4, as we already saw in previous slide. W0 is now simply equal to alpha, which in this case is equal to zero point 0.5. This we can clearly see is actually the initial value of the given initial value problem, that is the response of the system at t equal to 0 time step. Next we compute the quantity K1, which is used in solving the RK4 solver, and this is simply equal to h times the function evaluated at ti and wi. Uh, so this will become step size, which is zero point 0.2 times the function value at t naught w naught is equal to zero point 0.2 times the function value at 0, 0.5, 0.5 being w naught and t being 0, since we are still at the zeroth iteration. This simply becomes zero point 0.2 times 0.5 minus 0 square plus 1, or zero point 0.3. Now, the values of W0 and K1 will be useful in calculating for the other parameter K2. K2 becomes h times f of evaluated at Ti plus h by 2, Wi plus K1 by 2. And this equals zero point 0.2 times f at T0 plus zero point 0.1 and zero point 0.5 plus 0.15. This becomes equal to zero point 0.2 times the value of the function evaluated at 0.1, 0.65, which is simply equal to zero point 0.2 into 0.65 minus zero point 0.1 square plus 1, which is equal to 0.328. Next, we must use uh, the values of the quantities W0 and K2 to evaluate the quantity K3. And as per the given formula, K3 becomes simply equal to h times the value of the function evaluated at Ti plus h by 2 and Wi plus half K2. which is to say we multiply the step size zero point 0.2 times the value of the function evaluated at 0 plus zero point 0.1 and zero point 0.5 plus 0.164. This becomes equal to zero point 0.2 times 0.664 minus zero point 0.1 square plus 1, which is equal to 0.3308. And finally, the parameter k3 and w0 will be useful in evaluating the parameter k4. This becomes equal to h times the value of the function evaluated at ti plus 1 and wi plus k3. This is equal to zero point 0.2 times the value of the function evaluated at t naught plus h and wi plus k3. Here we see that we have now proceeded in the time discretization by the entire step series. This is equal to zero point 0.2 times the value of the function evaluated at 0.2 comma 0.8308, which comes out to be zero point 0.2 into 0.8308 minus zero point 0.2 square plus 1, which is equal to 0.35816. Now, at the end of the zeroth iteration, we have evaluated all 5 quantities that are useful: W0, K1, K2, K3, and K4. Now, these will be useful in calculating the values of these quantities for the next iterative step, that is at I equal to 1. We know that W1 is equal to W0 plus 1/6 times K1 plus 2K2 plus 2K3 plus K4. That is to say, the value uh, of the solution W1 is equal to the value obtained at the previous step incremented by some weighted average of the 4Ks that we calculated. And in this case, the value of the variable w at the iteration 1 is simply equal to 0.5 plus 1/6 times zero point 0.3 plus 2 times 0.328 plus 2 times 0.3308 plus 0.35816, which is equal to 0.829293. I have also calculated the exact value of W at the end of this iteration, and this should be equal to 0.8292986. Thus, the relative error is of the order of 10 power minus 6. Now, for this iteration, I equal to 1, we can further evaluate the other quantities k1, k2, k3, k4, which will again be useful in the next iteration. So, k1 equals h times the value of the function evaluated at ti and wi, which is equal to zero point 0.2 times the value of the function evaluated at zero point 0.2 and 0.829293, which is equal to zero point 0.2 times 0.829293 minus zero point 0.2 square plus 1, which is equal to 0.3578587. Now calculate the quantity K2. It is equal to h times the value of the function evaluated at ti plus h by 2 and wi plus half k1, which is equal to zero point 0.2 times the value of the function evaluated at zero point 0.3 comma 1.00822226. This is equal to zero point 0.2 times 1.0082226 minus zero point 0.3 square plus 1, which equals 0.3836445. Next, we must again calculate for this iteration the value of the parameters k3 and k4. For k3, it is equal to h times the value of the function evaluated at ti plus h by 2 and wi plus half k2. This becomes equal to zero point 0.2 times the value of the function at 0.3 comma 1.0211156 is equal to zero point 0.2 times 1.0211156 minus zero point 0.3 square plus 1, which equals 0.3842312. Finally, for this iteration, we must calculate the value of the parameter k4, which is equal to h times the value of the function evaluated at ti plus 1 and wi plus k3, which is equal to zero point 0.2 times the value of the function evaluated at zero point 0.4 comma 2155164, which equals zero point 0.2 times 1.2155164 minus zero point 0.4 square plus 1. This comes out to be 0.4111033. Now with all these quantities calculated, that is W1, K1, K2, K3 and K4, based on the RK4 method, we can now calculate the value of the variable W at the end of the second iteration, and that is equal to the value of W at the previous iteration incremented by a weighted average of these quantities K1, K2, K3 and K4. So W2 becomes W1 plus 1/6 times K1 plus 2K2 plus 2K3 plus K4, which becomes equal to 0.8292933 plus 0.3847829, which comes out to be 1.2140762. Again, at the end of this step, the exact value of W2 is equal to 1.2140877. Thus, the relative error again is of the order of 10 power minus 6. Next, we'll be discussing something called the Adams-Bashford methods, and we'll be working with both the explicit and the implicit methods. But before that, let us take just a short break, and when we resume, we'll be discussing the implicit and explicit Adams-Bashford methods. Good evening and good evening and welcome back to the live session. Let us review my lesson. We discussed the open and closed Newton codes methods, and now we'll discuss the class of methods known as the Adams-Bashforth methods. And here we have both the Adams-Bashforth explicit and implicit methods. We have already touched upon this topic in one of the previous sessions, but just to remind you, an explicit method is one where the quantity to be estimated, say the value of the variable, at the current time step can be expressed entirely as an expression of previously known quantities, such as the value of the variable at the previous time step at various spatial coordinates, and so on. That is to say, in the current iteration, we already have all the information needed to obtain or arrive at the value of the unknown variable. Whereas in an implicit method, the equation which describes the relationship between the known and unknown quantities has unknown quantities on both the LHS and RHS, and in the general case, it will not really be possible to just end up with a simple algebraic expression of the unknown quantity expressed purely in terms of all other known quantities at a given time step. So while we have a relationship for the unknown quantity, it is given implicitly. That is, the relationship cannot be simplified to obtain a simple algebraic expression. First, we'll discuss the Adams-Bashforth two-step explicit method, where clearly we arrive at the solution in two steps. Here, the quantity W0 is alpha, W1 is alpha 1, and Wi plus 1 is equal to Wi plus h by 2 times 3 thrice the value of the function at ti comma Wi minus the value of the function at ti minus 1 Wi minus 1, where I equals 1, 2, 3 till n minus 1. The local truncation method is given by 5 by 12 third derivative of y evaluated mu I times h square for some mu I belonging to the open interval ti minus 1 ti plus 1. The Adams-Bashforth three-step explicit method involves three previously known or given quantities W0 equals alpha, W1 equals alpha 1, and W2 equals alpha 2. Then, for the current iteration Wi plus 1, the value of the variable is obtained as Wi plus h by 12 times 23 times the value of the function at ti comma Wi minus 16 times the value of the function evaluated at ti minus 1 Wi minus 1 plus 5 times the value of the function evaluated at ti minus 2 Wi minus 2. In this case, the local truncation error is given by 3/8 fourth derivative of y evaluated at mu I times h cube. As we see, depending on the number of steps in the explicit method, we require information of as many previous time steps. For instance, for the two-step method, when calculating the I plus 1th iteration, we needed information from the ith and I minus 1th iteration. When solving for the three-step explicit method, the solution of the variable at the I plus 1th iteration required information at the ith, I minus 1th, and I minus 2th iteration. Since in the normal course of the solution, this information will be available to us. These are explicit methods. And for the very first iteration, that's why the values W0 and W1, or in the second case W0, W1 and W2, must be provided a priori. There is also the Adams-Bashforth four-step explicit method, where we make use of information from four previous time steps to solve for the variable, unknown variable at the current time step. W0 is alpha, W1 is alpha 1, W2 is alpha 2, and W3 is alpha 3. For the current iteration, Wi plus 1 is given as Wi plus h by 24, 55 times the value of the function at ti comma Wi minus 59 times the value of the function at ti minus 1 Wi minus 1 plus 37 times the value of the function at ti minus 2 Wi minus 2 minus 9 times the value of the function at ti minus 3 Wi minus 3. Here, the local truncation error equals 251 by 720, fifth derivative of y evaluated at mu times h power 4 for some mu I belonging to the open interval ti minus 3 and ti plus 1. There is also the Adams-Rashford five-step explicit method, where now we are making use of the information available at five previous time steps. And for the current time step, the unknown variable wi plus 1 is given as wi plus h by 720, 1901 times f at ti comma wi minus 2774 times the value of the function evaluated at ti minus 1 wi minus 1 plus 2616 times the value of the function evaluated at ti minus 2 wi minus 2 minus 1274 value of the function at ti minus 3 wi minus 3 plus 251 times the value of the function at ti minus 4 wi minus 4. In this case, the local truncation error equals 95 by 288, the sixth derivative of y evaluated at mu times h power 5 for some mu I belonging to the interval ti minus 4 ti plus 1. Now, all the Adams-Bashford methods were explicit methods, and we also have a separate class of methods called the Adam-Moulton methods, which are implicit methods. Implicit methods are derived by using ti plus 1 and the value of the function at ti plus 1 and y at ti plus 1 as an additional interpolation node in the approximation of the integral ti to ti plus 1 f at t comma yt dt. And some of the common implicit methods are as follows. First being the Adams-Moulton two-step implicit method, where W0 is alpha and W1 is alpha 1. For the current iterative step, the value of the unknown variable Wi plus 1 is expressed in terms of Wi plus h by 12 times, 5 times value of the function at ti plus 1 Wi plus 1 plus 8 times the value of the function at ti comma Wi minus the value of the function at ti minus 1 Wi minus 1. We see here that the unknown variable wi plus 1 is on both sides, on the left side in itself and on the right side uh, implicitly embedded into the value of the function to be evaluated at that step. Here the local truncation error is equal to minus 1 by 24 times the fourth derivative of y evaluated at mu times h cubed. We also have an important note on the implicit and explicit methods. It says that in general, the coefficients of the terms involving the function f and the local truncation error are smaller for the implicit methods than for the explicit methods. And often this leads to greater stability and smaller round of errors for the implicit methods. And because of this, we also have greater flexibility in choosing the time step for implicit methods while ensuring convergence. And we can in fact work with larger time steps in an implicit method, thereby saving computational effort. However, this choice between implicit and explicit methods is not always black and white. Sometimes it is quite gray. For example, for people working in solving fluid flows, if you make use of a method called the volume of fluid method, you will find that in certain cases, it is actually prescribed and preferable to use explicit methods rather than implicit methods to ensure convergence and accuracy both. So the exact choice of whether the time discretization or say any other discretization like the view of discretization is implicit or explicit depends on your actual use case. There is also the Adams-Moulton three-step implicit method, where we must start with the knowledge of a priori of three quantities: W0 equals alpha, W1 equals alpha 1, and W2 equals alpha 2. Wi plus 1 is given as equal to Wi plus h by 24 times 9 times the value of the function at ti plus 1 Wi plus 1 plus 19 times the value of the function at ti comma Wi minus 5 times the value of the function at ti minus 1 Wi minus 1 plus the value of the function at ti minus 2 Wi minus 2. In this case, the local truncation error is equal to minus 19 by 720 fifth derivative of y at mu I times h4 for some mu I belonging to the open interval ti minus 2 ti plus 1. Next, we have the Adams-Moulton four-step implicit method, where the value of four quantities must be known a priori. those being W naught equals alpha, W1 equals alpha 1, W2 equals alpha 2, W3 equals alpha 3. In such a case, the value of the unknown variable W at the current iterative step, Wi plus 1 will be given as Wi plus h by 720 times 251 times f at ti plus 1 Wi plus 1 plus 646 times the value of the function evaluated at ti comma Wi minus 264 times the value of the function evaluated at ti minus 1 Wi minus 1 plus 106 times the value of the function evaluated at ti minus 2 Wi minus 2 minus 19 times the value of the function evaluated at ti minus 3 Wi minus 3. In this case, the local truncation error is equal to minus 3 by 160 times the sixth derivative of y at mu I times h power 5 for some mu I belonging to ti minus 3 comma ti plus 1. Now, we return back to the same initial value problem that we solved before using the RK4 method, and now we will try to solve it using the explicit Adams-Bashforth 4-step method and the implicit Adams-Moulton 3-step method, and we'll compare the two solutions. So, I request the participants to take a minute to absorb the question and try to start solving it using the formula provided in the slides. And after that, we'll get on with the solution. Let's get started with the solution. First, we'll arrive at the solution using the Adams-Bashforth 4-step explicit method, and the formula is already given here. For the current iterative step, Wi plus 1 will be evaluated as Wi plus h by 24 times 55 into the value of the function at ti comma Wi minus 59 times the value of the function at ti minus 1 Wi minus 1 plus 37 times the value of the function at ti minus 2 Wi minus 2 minus 9 times the value of the function at ti minus 3 Wi minus 3. Here the step size is 0.2, ti is 0.2 and the value of the function at any t comma y is given as y prime equals y minus t square plus 1. This will give us the value of the variable w at the current time step as 1 by 24 times 35 wi minus 11.8 wi minus 1 plus 7.4 wi minus 2 minus 1.8 wi minus 3 minus 0.192 I square minus 0.192 I plus 4.736. With the Adam Moulton 3-step implicit method, the value of the variable w at the current time step I plus 1, iterative step I plus 1 will be equal to wi plus h by 24 times 9 into value of the function at ti plus 1 wi plus 1 plus 19 times the value of the function at ti, wi minus 5 times the value of the function at ti minus 1 wi minus 1 plus value of the function at ti minus 2 wi minus 2. Here the definition of the step size and the function at any t comma y remain the same. And so wi minus 1 equals 1 by 24 into 1.8 times wi plus 1 plus 27.8 times wi minus wi minus 1 plus 0.2 times wi minus 2 minus 0.192 times I square minus 0.192 times I plus 4.736. Now in this case, despite this being an implicit method, because this is an implicit method, we see that we have wi plus 1 on both sides of the equation, in both the LHS and RHS. And this being one of the simpler cases, it shows that we can bring wi plus 1 to the left hand side to obtain something like an explicit expression for wi plus 1. However, in general, this will not be the case. And here we have tabulated the exact value of the function at few time steps, and the value of the function approximated by the fourth order explicit Adams-Weishaupt method and the third order implicit Adams-Moulton method. In each case, we see that the error of the implicit third order implicit Adams-Moulton method is far smaller than the fourth order explicit Adams-Weishaupt method, despite being one order lower, thereby saving computational resources. But what is this dichotomy between explicit and implicit methods, and which one do we actually end up using? The implicit methods usually give better results than explicit methods of the same order. However, these implicit methods have the inherent weakness of first having to convert the method algebraically to an explicit representation for wi plus 1 as we did in the previous example. However, this procedure might not always be possible. The example that we solved was one of the simpler cases, and so would actually have an expression for wi plus 1, a simple algebraic expression. However, in general, this will not be true. In practice, therefore, the implicit multi-step methods are not used directly. Rather, they are used to improve approximations obtained by other explicit methods. The combination of an explicit method to predict and an implicit method to improve or correct a prediction is called a predictor corrector method. And here we have the pseudocode for an Adams fourth order predictor corrector method, which combines the uh, good features of both of these methods. Here again, we are trying to find the solution of the general initial value problem y prime is equal to f of t comma y, where a less than equal to t less than equal to b, and y at a is given as alpha at n plus 1 equally spaced nodes enclosed a comma b. The input of such a code would require the endpoints a b, the integer n, and the initial state alpha. The output of such a program would be the approximation w to y at the n plus 1 values of I. In the first step, we set the time step, that is h is equal to b minus a by n, t naught is equal to a, and w naught equal to alpha, and we also output t naught comma w naught. In the second step, we start looping, uh, set for I equals 1, 2, 3, two steps 3 to 5, and the use of this loop is to actually compute the starting values uh, for the methods using the RK4 method. In the third step, we set k1 equals h times the value of the function at ti minus 1, wi minus 1, k2 equals h times the value of the function at ti minus 1 plus h by 2, wi minus 1 plus half k1, k3 equals h times the value of the function at ti minus 1 plus h by 2, wi minus 1 plus half k2, and k4 equals h times the value of the function at ti minus 1 plus h, wi minus 1 plus k3. In the fourth step, we set wi equals wi minus 1 plus 1 6 k1 plus 2 k2 plus 2 k3 plus k4, and we also set ti equals a plus ih. In the fifth step, we output ti comma wi. In the sixth step, we start a second loop to loop through the steps 7 to 10 and start the iteration counter from I equals 4, 5 till n. We set t equals a plus ih, that is the incremental time step. W is approximated as W3 plus h by 24 times 55 into value of the function at t3 comma W3 minus 59 times value of the function at t2 comma W2 plus 37 times value of the function at t1 comma W1 minus 9 times value of the function at t0 comma W0. That is, we are using an explicit formulation to predict the value of W and the current time step. Next, we correct this predicted value as W equals W3 plus x by 24 times 9 times the value of the function at t comma W, since W is already known to us from the previous explicit step, plus 19 times the value of the function at t3 comma W3 minus 5 times the value of the function at t2 comma W2 plus the value of the function at t1 comma W1. Thus, we are correcting the predicted value using an implicit scheme. In the 8th step, we output t comma W. In the 9th step, we set the iteration counter j equals 0, 1, 2. We set tj equals tj plus 1 and wj equals wj plus 1. Next, we update the time step. In step 10, we set t3 equals t and w3 equals w. Finally, in step 11, after looping through steps 7 to 10, we stop the program. We will also use this Adams fourth order predictor corrected method with the step size h equals 0.2 and starting values from the RK4 method that we already solved. To the initial value problem, y prime equals y minus t square plus 1 for 0 less than equal to t less than equal to 2, and the value of the function y at 0 equals 0.5. Since we have already solved this, we know that from the RK4 method, y0 was equal to w0 equals alpha was 0.5, y at point 2 was approximately equal to 0.8292933, y at point 4 was approximately equal to 1.2140762, and y at point 6 is approximately equal to 1.6489220. Now we use the predictor corrector, fourth order predictor corrector method, and the first step is to find or predict the value of y at the next time step pointer using the explicit scheme. This is approximately equal to W4P, where P stands for predicted, equals W3 plus 0.2 by 24 times 55 value of the function at 0.6 comma W3 minus 59 times value of the function at 0.4 comma W2 plus 37 times value of function at 0.2 comma W1 minus 9 times the value of the function at 0 comma W0, which comes out to be 1.6489220 plus 0.2 by 24 times 55 into value of function at 0.6 comma 1.6489220 minus 59 times value of the function at 0.4 comma 1.2140762 plus 37 times the value of the function at 0.2 comma 0.8292933 minus 9 times the value of the function 0 comma 0.5, and the predicted value thus becomes 2.1272892. Next, we correct it using the implicit step plus y of 0.8 is approximately equal to W4 is equal to W3 plus 0.2 at 24 times 9 times the value of the function at 0.8 comma W4 predicted plus 19 times the value of the function at 0.6 comma W3 minus 5 times the value of the function at 0.4 comma W2 plus value of the function at 0.2 comma W1. This comes out to be 2.1272056. If you compare this with the we see that the predicted corrector method has the error which is 2.39 into 10 to the power minus 1. Whereas for RK4, the error was 2.69 into 10 to the power minus 5. So they are comparable for this particular example. Lastly, we'll discuss the stability of these multi-order methods, and this is an important theory with which I would like to close the session. So the general multi-step method, such as the ones we have been solving, for approximating the solution to the initial value problem, y prime equals function of t comma y, for a less than equal to t less than equal to t, and y at a equals alpha, has this form: w naught equals alpha, w1 equals alpha n, wn minus 1 equals alpha n minus 1, and wi plus 1 equals am minus 1, wi equals am minus 2, wi minus 1, and so on to a naught wi plus 1 minus n plus h times some function of ti h wi plus 1 wi to wi plus 1 minus n. Here a naught a1 till a plus am plus 1 are constants, and as usual h equals b minus a by n and ti equals a plus I. Now associated with this equation, w naught equals alpha, w1 equals alpha 1, w1 minus 1 equals alpha plus 1, wi equals plus 1 equals am minus 1, wi equals am minus 2, wi minus 1, and so on till a naught wi plus 1 minus n plus hf bi comma h1 wi plus 1 wi till wi plus 1 minus n. There is a polynomial called the characteristic polynomial of the method given by p of lambda equals lambda power m minus am minus 1 or lambda m minus 1 minus am minus 2 lambda power m minus 2 minus a1 lambda minus a naught as given in equation 5.58, and the stability of a multi-step method with respect to the round of errors is dictated by the magnitude of the zeros of this characteristic polynomial. Let alpha lambda 1 lambda 2 till lambda m denote the roots of the characteristic equation, and these roots are not necessarily distinct. Associated with the multi-step difference method, w naught equals alpha, w1 equals alpha 1 till w1 minus 1 equals alpha n minus 1, and wi plus 1 given as a function of these wi's. If the magnitude of lambda I is less than or equal to 1 for each I equals 1, 2 till m, and all roots with absolute value 1 are simple roots, then the difference method is said to satisfy the root condition. Methods that satisfy the root condition and have lambda equals 1 as the only root of the characteristic equation with magnitude 1 are called strongly stable. Methods that satisfy the root condition and have more than one distinct root with magnitude 1 are called weakly stable. Methods that do not satisfy the root condition are called unstable. Consistency and convergence of a multi-step method are closely related to the round of stability of the method. And with this, we come to the end of the live sessions for this week, as well as to the end of the live sessions. For this run of the course AE03 on Computation Science and Engineering, it was a pleasure to have all of you in this course and to assist Professor Day, who was so kind as to give me this chance to be a TA for this course. It was a great learning experience for me, and I hope your experience was also something similar. Professor Day, of course, uh, has poured a lot of knowledge and effort into his lectures, and they alone are sufficient to have a very good working knowledge of such computational methods and the actual science which goes behind implementing these techniques in a commercial package. And as a teacher, it was my role to illustrate some of these concepts and to reinforce them with illustrious examples and to help you with the assignments and the certification examination should you have registered for it. So I had a very fruitful experience. I thank you all once again for tuning in to week 8 of the live sessions for the NPTEL course on Computation Science and Engineering, as well as for tuning in every week over the past 8 or 9 weeks. I look forward to seeing you again in the next run of this course. Thank you very much. This is Sourav Goswami from IIT.